Hi, my name is Diana Inostroza, and this is my project, Point of Interest Information Retrieval System for Tourism. This information retrieval system it aims to help people find points of interest like museums, parks, iconic sites, and monuments across 5 cities: Madrid, Barcelona, London, Paris, and New York. The underlying reviews are straight from TripAdvisor.es, so they are mainly in Spanish, but they mix a little bit of English. The core problem is a vocabulary mismatch problem. If I search for parques gratuitos, free parks, a document that says entrada sin costo or acceso libre means the same thing, but keyword search won't catch the exact match. My corpus is 2,000 TripAdvisor point of interest reviews. Uh, I used 400 per city. Each document has a point of interest name, a city label, and the review text. I designed 10 Spanish queries that cover different tourist interests, such as sightseeing, photography, family activities, architecture, romantic dining, and so on. Here's my script where I create the corpus, and this is a little preview of what the corpus looks like pre editing. So following, I go to my project is broken down in 5 layers. In the layer one, what I mainly do is text processing or pre-processing and the indexing layer. I use a snowball stemmer specifically tuned for Spanish and a combined bilingual stop word list, including domain-specific ones I added like mejor, gran, and muy, which are common in TripAdvisor reviews but don't carry any retrieval signal. I then also build an inverted index and TD-IDF vectors that analyze the top terms per city and rank the top 5 documents using cosine similarity. So here's a quick preview of my code. I load, I process my data. These are just helper functions that help me break out the corpus, the unique point of interest. Here's my pre-processing pipeline with my snowball stemmer for Spanish, and then my inverted index and my vectorization. So after this, I do like a quick analysis of the common and rare terms. So we have some very common, then we have some rarer terms here. And then I just save the corpus and move on to the next layer, which is layer 2. It's a sparse retrieval using BM25. In this layer, we load the pre-processed tokens as well as the queries. It runs 2 configurations: default, where K1 equals 1.2 and B equals 0.75, and tune, where K1 equals 0.9 and B equals 0.3, which applies stronger length normalization. Each retrieves the top 20 candidates. So here are my outputs. Here's my pre-processing timeline that I just mirrored from the previous step. Here's where I build the index, load queries. I do this is my function for retrieval and where I run them. And then I inspect my top results and my score distribution analysis. Top 1 score per query, default versus tune. So they're very, very similar, but default does better in most of my queries. I have my QRails pool and my evaluation. and the precision recall curve. And this is a precision recall curve for BM25 on query 1. The y-axis is precision, and how many retrieved results are actually relevant, and the x-axis is recall, how many of the total relevant documents have managed to find. You can see precision starts high, how many of the total relevant documents have managed to find, meaning BM25 is getting relevant results at the top and then gradually drops as the ranking dips deeper into the corpus. The area under the curve is essentially what MAP is measuring across all of our queries. Then I save the run files and move on to layer 3. In layer 3 is my phase sense retrieval, which semantically matches similar documents. Instead of matching keywords, this uses neural embeddings. I'm using the All-Mini LML6v2 model from Sentence Transformers. It produces 384-dimensional vectors. I L2 normalize them and use phase index flat IP, which does exact cosine similarity search. Here's the steps. I load the corpus, build embeddings. I build the phase index. Again, I load my queries. I run the phase sense retrieval. And I inspect my top results. It does particularly well for this query 10, Paseo de Arquitectura en Barcelona. You can see the results are pretty on point. For example, here, Parque Güell in Barcelona, and all of these seem to be perfect examples. Okay, so here's my BM25 versus phase overlap analysis. In here, we measure how many top 10 results phase shared with BM25 default per query. The average overlap is 2.3/10. The lower overlap indicates the two retrievers are complementary. Therefore, fusion will add value. So moving on to layer 4. In layer 4, this is rank fusion. This is where I combine the BM25 and PHY's result lists. I implemented 4 strategies: reciprocal or rank fusion, which is my main one, plus COMSUM and COMB-MNZ, and weighted linear combination. The idea is that BM25 and PHYs find different relevant documents, so combining them gives better coverage. Well, let me walk you through the steps. First, I load the result from the previous layers. I load my judgments. Here, I've already judged manually each query to identify which were relevant and which were very far from relevant. Here's where I run RRF, COMSUM, COMB-MNZ, and weighted linear combination. Then I evaluate all methods. Based on the map results, the best fusion method is weighted configuration of 60/40, favoring BM25. However, none of the fusion methods actually beat BM25 default on map, which makes sense given that PHYs has weak city name recall. It introduces noise when it retrieves semantically similar documents from the wrong city. In a qualitative review of RRF, top results, here, let me pull that up. Here, we can see that RRF outperforms on individual queries. where semantic matching adds real value, like the architecture query here, as well as the romantic dining in, or romantic sites in Paris. I think all of these performed really well. Ile de la Cité, if anyone is interested. And moving on to my last layer, layer 5 is a cross-encoder re-ranker. This is the most powerful, but also the most computationally expensive step. It takes the top 20 results. It takes the top 20 fused candidates and rescores each one by jointly encoding the query and the document together as a pair. I am using MS Marco, a mini LM L6V2, which was trained specifically for passage ranking. And then I also extract a snippet later, the most relevant sentence from the review to show in the results. And here I will show you the demo. Okay, so I'm going to run this, and I need to input a query. I will type in Spanish, mejores monumentos de Londres. Londres. This just means best monuments in London. And here my system is running. Each model is being run. Mejores monumentos de Londres. We have Torre de Londres as top 1 and 2. Coca-Cola London Eye. The Monument to the Great Fire of London. Galería Nacional of London. Westminster. Arco del Triunfo. This one is not as relevant because of Paris. The city is mismatched, so this is noise. Monumento a los Caídos por España. This is Madrid, and then the next one is Barcelona. But we do see the top 1, 2, 3, 4, 5, 6 as highly relevant. So you can see the results here. The cross-encoder scores are on the right. Higher means more relevant, and below each point of interest name you get the snippet, which is the most relevant sentence pulled from the review. So going back to the numbers, here I pulled up the per query, the final pipeline evaluation for all prior methods. We can see that BM25 default has the higher map at 0.632, which tells you that BM25 is actually really strong at finding and ranking relevant documents early in the list. FIS alone scores lower, MAP of 0.153, but that doesn't mean it's bad. What it means is that FIS and BM25 are finding different documents. And on average, they only share about 2.3 out of 10 documents. So they are complementary. The cross-encoder pipeline does get the best NDCG at 10 at 0.616. NDCG is the metric that cares most about putting highly relevant documents at the top of the list. The cross-encoder is specifically trained to do that, so it makes sense that it wins in this metric. So now going down to the per query breakdown of the re-rank versus RRF. The cross-encoder improves over BM25 on 7 out of 10 queries, with an average NDCG improvement of about 0.078. So overall, the pipeline validates the core information retrieval principle. Each layer adds something. BM25 gives you strong keyword precision. FIS expands recall through semantics. Fusion combines both, and the cross-encoder puts the best documents at the top.